Hello, welcome to our new and Wolfram Language 12 webinar series. Today is the fourth and final session in our webinar series that has covered significant areas of new and expanded functionality in Mathematica and the Wolfram language. My name is Jamie Peterson. I'm the Technical Programs Manager for Wolfram U, a free and open learning hub that features interactive courses, video classes, and webinars like this one. Thank you for joining us today. Today, you'll be learning about the latest Wolfram language functionality for integrating with external languages, interfacing with real-world systems, interacting with blockchains, and compiling and optimizing code with the new Wolfram Compiler. Presenting for us today are Todd Gailey, Director of Engine and Connectivity Engineering, Suba Thomas, Software Engineer, Charles Poe, Manager of Discrete Computation, Christian Pascal, Connectivity Manager for Wolfram Research South America, and Abdul Dakak, Senior Compiler Developer. So before we get started with this very exciting and broad list of presentations, I'm going to go ahead and push a poll out that should be showing up on your screen. This asks you about your level of experience with Mathematica and the Wolfram language. Yep, okay, so 70% of you are currently using the Wolfram language, and that's great. That's kind of what we expected, but we do have about 9% brand new and others that have not recently used. So this is great. We're anxious to show you all the version 12 functionality today. Let's put another poll out. This one asks about the version that you're using, and many of you hopefully are already using version 12. That was released just a few weeks ago as we started this webinar series. Each new version of Mathematica and the Wolfram language includes new and expanding functionality, front-end enhancements, and system-wide performance improvements. So it's good to know from what point you're arriving at when you see this version 12 functionality today. Almost 70% are using version 12, the very latest version, but some stragglers with some older versions, and that's fine too. Hopefully we'll be giving you some good information that you can use today. Okay, that's all the information I needed to share. I think I'm ready to pass the microphone and the screen to Todd Gailey now, who's going to get us started with external system integration.
All right, hello everyone. My name is Todd Gailey and I'm the Director of Engine and Connectivity Engineering at Wolfram. I'll be talking today about features in version 12 of the Wolfram language that involve connectivity to other languages and environments. Although this is a new in 12 webinar, some of the things I'll be talking about are not actually brand new in 12. But we're present in 11.3, marked as experimental in many cases, still marked as experimental, by the way. But they're still quite new to the Wolfram world, and we want to make sure that people know about their existence and that you can make the best possible use of them. There are some changes and new features for version 12, and I will point those out as I go. There are also some new things coming in the future, which I'll try to mention as well. Wolfram has always recognized the importance of connectivity to other languages. We were an early innovator in this field with the development of JLink, our integration with Java, now coming up on its 20th anniversary. Followed that up with .NET Link for Microsoft's .NET platform. Those links provide an extremely tight integration with their respective languages, effectively making the Wolfram language a scripting language for Java and .NET. Of course, the world of computing changes rapidly. New languages rise and become important very quickly. There are many popular languages now, and some are especially important in certain niches. We now think that the best way to support a variety of languages is with a general framework that perhaps does not provide quite as tight an integration with the target language. It gives most users what they need to interoperate the way they want. That is the external evaluate framework. So one of the nicest features of the external evaluate framework is the so-called external language cells. If you just open a notebook and hit the right arrow as the first character in the cell, it automatically converts to an external language cell. The default is a Python cell, which you can tell from this little Python logo there on the left. So I can just type some arbitrary Python code in this cell, just as if I was typing at a Python prompt. Of course, Python knows how to evaluate 2 plus 2. So, I mean, this is a trivial example, but I don't want to, minimize the importance of this. You now can, you now have a Python cell type that lets you type arbitrary Python code, arbitrary Python computations into a notebook and evaluate them and get results back. Data types are converted in what we think is the most natural way when sending to Python or returning back to the Wolfram language. Obviously, that when I did 2 plus 2 a minute ago and I got 4 back, that was the number 4 in Wolfram language. Here I create a Python dictionary and return it. And that comes back as an association in the Wolfram language. All of the standard types that you might think are supported: numbers, lists, associations, and dictionaries are mapped. Here's a more complicated example. If I take a NumPy array, NumPy arrays come back as these numeric array expressions in Wolfram language. Now, numeric array is an experimental function in Wolfram in version 12. So you might not know about it. This is just about the only thing right now that uses numeric array that exposes it, but we'll be exposing this more in the future. It's the efficient array representation. We use numeric array because we might expect that these NumPy arrays would be large. I say normal of that. It converts it into a regular list. And here's an example where I use this pandas. This is a popular data science library in Python. I create a data frame. And this is really analogous. A data frame is very much analogous to a Wolfram language data set. So that is what it gets converted to automatically, Wolfram language data set. And of course, the reverse would happen as well. If I had a Python function that took a pandas data frame and I could pass it a data set from the Wolfram language, it would automatically be converted. It's not a feature. So it's very, very convenient and handy to have a cell type. You just type code in, just like you were typing in your favorite editor for that language. There's another way, which is the external evaluate function, which is more convenient if you're trying to write a program, if you're integrating Python code into Wolfram language programs. So here I just type external evaluate. I give the system name Python, and then I just a string of Python code. This is effectively sort of like calling to expression on some Wolfram language code. So evaluate that. So I'm just doing some, cumulative something and using some NumPy functions. Now notice I printed from Python and it comes back as print output in the Wolfram language. So it's quite convenient. Prints carried across, and I get back a numeric array. So if I wanted to use this in a program, well, trivially, I'm just going to, let's say I want to transpose it. So here's just a combined program where I'm using some Wolfram language functionality wrapping around a call to Python. And then there's my transposed array. Okay. Over here. Some troubleshooting. If you try external evaluate or external language cell and it doesn't work, you get some message about complaining about maybe some missing dependencies or some other thing about some other failure. It's likely that you either simply don't have the appropriate language installed or it's missing a required dependency. There's this find external evaluators function which you can use. You give it the name of the system you want, and that's what it returns for my system. As you can see, I don't even know why I have so many copies of Python installed on my system, but we know how to go out and find them, and so this is all the set of external evaluators I have. Now you notice in this one, it says missing dependencies. It's virtually certain. If you have Python, say, or NodeJS, or one of the other languages that are supported, if you have this installed in your system and it works from command line, but it doesn't work with external evaluate, and it's very likely that it's missing the 0MQ library. We require 0MQ as the communications mechanism between Wolfram and these other languages. Many languages don't come by default with the 0MQ library installed. So it's very likely that if that's the problem, that it's not working, but you have the language, that you don't have the 0MQ library for it. So that's the number one thing to try to install. You can also say there's also a register external evaluator function. So for example, in this list, when I do a Python cell, the first listed Python evaluator is when it's going to get used. I might want a different one. So if I wanted, say, my Python 2.6 or this 2.7, or whatever, my example is for this one. If I wanted this one, this Python 3 one, to be used instead, then I simply call register external evaluator, and that will push it to the top. I mean, it's already, my system already knows about this, but if I just call this function, it brings it to the top. So if I call this and then do another Python cell, then that evaluation will go to this evaluator. And we have documentation pages for configuring Python and configuring Node.js. Here's the, keep up on the window. Here's the page, the troubleshooting page for configuring Node.js and external evaluators. And this is exactly what I had to do. When I tried this Node.js for the first time, then it didn't work. It was precisely because of this missing 0MQ dependency. I just went through these steps, and then everything was fine. So we do have documentation to this, workflows for fixing these problems. All right. We have a new in12 function as part of this framework. It's called external function. External function, it's a Wolfram language function whose implementation is in an external language. It's like a handle to a function that's implemented in the external language. So in this example, this is Node.js. Switch over to Node.js for a moment. If you click on this icon, you might wonder, how do I get a Node.js cell? Well, you can click on this icon for these external language cells and pick one of the supported evaluators. So you just pick Node.js. So here's a Node.js function. This evaluation is smart enough to know that it was a function that was returned. Just evaluated to a function. So it returns this external function expression. External function, you know, and if you look at it, I'll open it up just for a second. It has all sorts of information about it. It shows what type of function it is. It actually shows the source code. And it shows the expression that this function is defined in. So I can simply, I'll call that F. And then if I can call F and I'll get the result. So I effectively defined a Wolfram language function called F, whose implementation resides in Node.js. It's pretty cool. You can also create an external function directly. You can just type it in. Now, in a previous example, I used a Node.js cell. And because when I evaluated that Node.js cell, the result of the evaluation was a function definition, I automatically got an external function object back in Wolfram language. But I can also just type external function in directly, just inline the source code, make an external function. I named it current date time, so I can just call it. This is a more convenient programmatic way to create external functions. You have to be a little careful with session management. And this is something of a tricky aspect of external evaluate in these external language cells. And at the moment, we don't have a great system for doing this type of management. We're going to change some things around and add some features for this. But for now, you have to be aware of some issues. So here, I'm going to manually create an external function. This is just built-in function len in Python. And then if I call it on a list, of course, it gives the right answer. Let's try something else. Let's create, if I just call, see here I called external function. If I just call external evaluate Python len, I get an external function back as well. So you think, okay, that's great. It works fine. External evaluate was smart enough to know that this was a function, and so it created an external function object. Call it. Whoops, didn't work. So what happened? The problem, and I'm explaining this to you, we're going to change this behavior, but you have to know it now, is that when you call external evaluate, when I make this call, that creates a Python session, starts one fresh, and kills it at the end. It's a one-shot thing. External evaluate is a one-shot thing. Doesn't use the same Python evaluator used by Python cells. So if I build up a bunch of state in Python through Python cells, and then I call, like some function definitions or something, and I call external evaluate and, Python, comma, and then try to call some of those functions, it won't work because it's starting up a fresh session. It's not the same session in which those functions were defined. So that's what's happened here. As soon as this external evaluate ended and this external function object was returned, that Python session was exited. When I try to call it, this message tells me that this external session object is not even valid anymore. So there's a simple solution to this, and just simply to always do direct session management. If I say there's a function called start external session, so now I have a handle to a persistent session. And I can use this instead of using this magic string Python as the first argument to external evaluate. I used this session reference. So now I'll just make that definition in this session, and now it works. So the important thing is that I created a long-lived exception called, with explicit name, and I used that. So it's quite convenient to just say external evaluate of, Python as a string, blah. But you have to remember that the Python session is going to be closed when that external evaluate finishes. So if you really want it to persist, create a session manually and use that as the first argument. Now, you're probably thinking, that's bad. That's a dumb idea. That's bad behavior for that Python session to exit. I agree. Definitely going to change that. So at some point in the future, probably the very immediate future, that will change. And external evaluate will not immediately exit the session that it's run. But for now, it does. So be aware of that. I think I have one more. Same thing here. I can also I make my own definition of some trivial Python function and then return it. I get an external function expression. Now I can call it. This is just an example of a function, inlining a function definition. All right. We do have more languages coming. Essentially, any language that has a REPL, a read eval print loop, can be supported in the external evaluate framework. We already have Ruby, Julia, Go, Haskell in the works. Java has a REPL now too, so we'll do this for Java and other languages. In fact, we'll probably document how to do it because it's well within the capabilities of a interested programmer to create one of these external evaluate plugins in effect for their favorite language. Right. Another feature that's new or changed in version 12 is for web browser control. And this is kind of a niche thing perhaps for many people, but it's really quite handy. In version 11.3, you could do this. I'm not going to evaluate this cell because it doesn't work anymore. You could use external evaluate with this, WebDriver-Chrome, sort of magic environment, and pass some sort of relatively obscure set of arguments to capture a web page. That capability has been eliminated. And it's replaced by a simpler, much more direct interface for browser control. So now I can just say web image and give the URL. In fact, I'm going to run this. I don't know. You probably didn't see anything because it didn't pop up on this screen. When you run this, the web browser launches and goes through whatever scripting operations are in the background and then finishes. So I can compare web image to this sort of obscure command line. You can do much more complex things. The main function is called web execute. You start a web session and you call web execute, and there are docs for web execute. They're long, and there's a huge number of these little keys that you can use to do all sorts of things. You can script button presses and form page submissions and all sorts of things. You can essentially script an arbitrary user interaction with the web browser. Quite handy for web testing or something like that. Web scraping. In this example, I'm just going to open a Wikipedia page and extract all the hyperlinks from that page. In the background, the web browser launches, and then here's this shortened, elided result of 81 different hyperlinks on that page. And then finally, I want to mention the Wolfram client library for Python. It's an extremely handy, powerful library. It's a new library. It makes it very easy to access Wolfram language functionality from Python. Now, this is not strictly a feature of version 12. It works in other versions of Mathematica and other versions of the Wolfram language. But it's out. It's new now. It's been out for a little while, but it's still quite new. It's open source, fully documented. You can find it on GitHub. But you don't have to do anything. You don't have to go make it or something off of GitHub. You can just say pip install Wolfram client and get it. I'm not really going to show any examples of this because I don't have time. But some things you can do, you can evaluate expressions in a local Wolfram kernel, the Wolfram cloud, or an enterprise Wolfram cloud. So it's quite handy. You can direct your computations either to a local kernel or a cloud kernel without really changing your code in any way. You can call Wolfram Cloud APIs. It's a convenient interface for calling Wolfram Cloud APIs. You can represent arbitrary Wolfram language expressions and programs in Python. It's like a very simple syntax. I wish JLink could have something as slick as that, but it's not Python for representing Wolfram language expressions. You can call built-in Wolfram language functions directly in Python. You can easily define native Python functions that call Wolfram language functions. There's all sorts of good documentation showing all these features. Here's a link to the library documentation. Here's, lovely examples of all these different types of functionalities. It's very simple to use. There's a link to a blog post announcing it. It has some other examples of its usage. And here's a link to the GitHub homepage. There are other client libraries to follow. There's a Java one that is just polishing up now. All right, I think that is the end of my presentation. So I'd like to pass it along now. Suba, who will be talking about the microcontroller kit. Thank you.
Thanks, Todd. So as Todd mentioned, I'll be talking about the microcontroller kit, which is new in version 12. So let me first spell out the outline for this presentation. It has three parts. I will start with an overview of how the microcontroller kit operates and what you need to get it up and running. Next, I will demo some building blocks using concrete examples. And finally, I will demo a sample project. So what I wish to convey as with this talk, as I drill down from a 10,000-foot view to examples and then a sample project, is that the microcontroller kit is on one hand a very straightforward tool, but on the other hand it's also very versatile and powerful, because essentially there is only one function that you will be using to deploy code to the various microcontrollers. So once you have what you want the microcontroller to do, you just have a uniform paradigm and you're specifying the code you want to deploy at a very high level. So it's the same paradigm that's repeated over and over again for the various microcontrollers and also the various computations you want to do on the microcontroller. So this is the workflow of the microcontroller kit. So it's a three-stage process. So it first generates the source code, and then it invokes a compiler to compile this code, and then it uploads that compiled code through using a programmer, through an external programmer, to the microcontroller. So the setup you need for that flows from this workflow. So of course you need the Wolfram language and the microcontroller kit. So I'm going to first load the microcontroller kit, and then you need a compiler. So the most straightforward solution is to install the Arduino IDE. So I already have the Arduino installed on my machine, and it's a Mac, so I just make sure that it exists. So what others, even if you're on a Mac or even if you're on a Windows or Linux system, you just have to install the Arduino IDE and the microcontroller kit will pick up the compiler toolchain. Yeah, in case you have a custom compiler toolchain or it's in some other location, it's just an option to tell microcontroller kit where to find the compiler. Okay. So as I mentioned, there is only one function that you use to upload the code, and that is microcontroller embed code. Okay. And it has three arguments. So this fourth argument is an assortment of optional specifications. So if you have a custom compiler installation, this is where you will specify that. And we'll also see some examples where we use these additional specifications. But essentially mostly there are three specifications that the microcontroller embed code takes. The first one is the systems model, or the core computation that the microcontroller needs to do. So I like to think of this as, what is the computation you want the microcontroller to do? And the second argument has to do with the microcontroller itself. So it answers questions like, which microcontroller do you want to send the computation to? Which inputs do you want to use? Which outputs? And other microcontroller specifications. And the third one is, where is this microcontroller located? So this may be like a connection port to which the microcontroller is connected to your PC. And this is the mechanism to get the compiled code onto the microcontroller. So let's start looking at some examples. So this is the simplest example. I want to blink an LED. So the first argument is the systems model. And I want to blink an LED connected to pin 3. So I'm going to connect that LED right now. So I connect the one end of the resistor to ground and the other one to pin 3. Okay, so I have this setup here, and now this is the computation I want to do. If the level of that pin is above 0, I turn it to 0, and if it is 0, I turn it on. It's basically a pulse. And then, so that's the first argument. In the second argument, I say that my target is an, let me focus on that the target is an Arduino Uno, and the output I'm using is output 3, and it's a digital output. And this is the port to which this microcontroller is connected to my Mac. So now if I evaluate that, oops, what happened? Should work if all the connections are right. I think I have my ground. Sorry about that. I had my ground pin connected incorrectly. But now you should see the LED blinking. And it returned this microcontroller code data object from which I can get additional properties. So I can take this object and then ask for properties, and it'll have a whole slew of properties, and from this I can get what was the source code and so on. So let's modify this just a little bit. So instead of turning this LED on and off, I want to send an analog output. That is, it's the value that is sent to the LED is continuously varying from 0 to 5 volts. So in this case, and I'm adjusting that value using a potentiometer. So let me connect the potentiometer, and hopefully this time I don't mix up my pins. I connect one end of the potentiometer to ground, the other end to 5 volts, and the wiper pin to A0. Now the value that the potentiometer reads, I want to send directly to the LED. So the systems model is just a unity gain of 1. And now my target is again Arduino Uno. The input is from the analog pin A0. It's an analog input. And the output is again digital pin 3, but instead of being a digital output as it is outputting now, I want it to be an analog output. And then I'm going to evaluate this. And now, okay, once it's done, if I adjust this, you can see the LED. I don't know how clear it is with the lighting in this room, but you should see the LED increase in brightness and be turned off. Okay. So I'm going to do a little more involved example. So here I have an Adafruit Metro. Let me get that set up out. Okay. So here I have an Adafruit Metro that is connected to a MAX 6675 temperature sensor, and this is a temperature sensor, and I want to output the result onto an LCD through a backpack. So the input is just simply passed to the output. So as before, I have a unity gain 1. Now here, this is an SPI input. So as before, it's not just one input through which one pin through which the input is coming in. So because this is an SPI device, the input is coming in through pin 12, which is master input slave output pin. So this device is a slave, and through its slave output pin, it's sending the output to pin 12. That's why I have the input the input is coming through pin 12 and it's of type SPI. Now this microcontroller needs to request that data from this device. And to do that, it needs to set the slave output pin of this device to the chip select pin of this device to be low. So the slave output pin is the pin through which the output is sent, and the chip select pin is what needs to be set low by the microcontroller for this device to start sending the result. So I've chosen pin 7 as the pin to trigger to start the device to start sending output. So once let me evaluate these. So once microcontroller embed code sees this, it knows that it needs to configure this microcontroller itself as a master SPI device. Okay, and once it does that, it sets pin 13 as the clock pin. That's fixed. It's from the data sheet. That's the clock pin, and I connect that pin to the clock of the sensor. And the other two connections are the ground and the 5-volt power lines. Okay, but that is not the end of the story. So once that is set up, the microcontroller also needs to know how many bytes to request from the device and what to do with that. And this comes from the data sheet of the sensor. The data comes in as 2 bytes. So I'm going to give the specification of the device as the slave select pin 7, and it has to read in 2 bytes. It's going to select that is bring that pin low, and then it's going to read 2 bytes, and then it's going to use that 2 bytes to compute the temperature using this incantation. Yeah, this information all comes from the data sheet. So to summarize, for the input channel, the data is coming in through pin 12. It comes in when the microcontroller sets this chip select pin low, and then the microcontroller computes the reads in 2 bytes and computes the temperature using this code. So that's all for the input channel. Now the output. Yeah, the output I've connected through this Adafruit LCD backpack, and it uses I2C communication. So I2C is in the specification is somewhat similar to SPI, but I decided to use the library that is provided by Adafruit. So when we use the library, so first thing we need to do is install the libraries. So that's the standard way you install it for install any Arduino library. So I've already installed it and it exists. And when we are using the library, we do not really understand the I2C specification, but we need to understand the library. And this is the only time when you'll be writing explicit code, because you have to inject that code into the code that is being automatically generated by microcontroller embed code. So this is the general program layout. And this library code has to be injected into various segments of this program. So to get this LCD backpack to send the values to this LCD, we need to include these header files. One is the I2 wire header file, and then is the header file for the liquid crystal display itself. And then this is where we create the object, and then we begin to initialize that LCD. It's a 16-character LCD with 2 rows of values. I set the backlight to be high. I set the cursor to location 2, that is the second character in line 0, and I print the value temperature. So this, when I send this program, this is what is going to first happen. And then in a loop, what needs to happen is the actual output channel. So this is of type external library, and then I'm telling what the microcontroller needs to run in a loop. The value that it receives, it assigns to the variable temp. It sets the cursor to position 4 and in line 1, so that is over there. And it prints that value, and this is printing degree centigrade. So all this the input, outputs, and everything we need, and all the utilities and initialization is that gives the complete microcontroller specification. And now I'm ready to deploy the code. So here is where I use the fourth argument. So this is the fourth argument, and the fourth argument I need to specify where it can find the library and also the details about the SPI device. So if I evaluate that, oops, it's kind of a little warm in this room, but I have a cup of ice here, and if I dip it in, you should see the temperature drop. I have an ice cup here. Okay. So now let's look at a sample project. So here I have, let me get that motor out. Yeah. So my objective is to deploy a controller to regulate the speed of this motor. So yeah, for this talk, I'm not going to go how I obtain the controller. So you can find more details on that in the documentation. But this is the controller has two inputs. So the first input is coming from this potentiometer here that I've connected to pin 2, and that is setting the reference speed that the motor needs to run at. Okay, so let me get the controller. So the first input is the analog input that the motor needs to, that gives the reference speed of that I need the motor to turn. And then the second input is the actual speed of the motor, and that is coming through an encoder, which I've connected to pin 2. So this is a series of pulses. So the more number of pulses implies that the motor is going faster. And we can count the number of pulses by counting the rising edges or the falling edges, or even the number of times it's toggling. I've chosen to count the number of rising edges. So this is a very high level specification. We just say we need to count the number of rising edges, and that will tabulate, that we convert using this block here to the speed of the motor in RPM. So that is the inputs. And the output, it's an analog output that is being sent so this goes through the motor shield, and that is what is sending the speed. It's an analog signal, just like it's the same thing as when I was adjusting the brightness of the LED. It's exactly the same thing, except that over there it ran from 0 to 5 volts. So 5 volts filled up the register with the value 255. But over here, my max value is 100. That's the duty cycle the motor has to run it. So at that value, the motor will go at full speed, or that register will be full. So it's an additional option we give. And then I have two additional outputs here because I want to actually bring the speeds back into Mathematica and be able to visualize it. So again, if you see the paradigm, it's the computation we want to do, the input channels and the output channels. And then there should be two. Let me evaluate it. So now if hopefully you can see the motor going faster as I pick it up. And now I would like to visualize. Now I can see that the motor is responding to my thing, and even if I give some disturbance, you can see it's resisting the disturbance and trying to maintain the speed. But I would like to actually see what these actual values are. And that's my motivation for having these two serial outputs, so I can bring them back into Mathematica. But you can connect any serial application to it. You can connect either screen or even the Arduino IDE to see those values. But here I've used the device framework in Mathematica. So I'm going to open a connection to that port. And now I'm going to start reading the values. So let me set it to some value. So how the data is coming in is there is a start byte, then there's a delimiter, and there's an end byte. And that is like the data in one sampling period of the controller. So this has both the reference speed and also the actual speed. And there is a delimiter byte. So I split it and I get the two values, and this is coming in ASCII codes. Oops. Okay, let me flush it. It should not be 0. Yeah, so this is the current speed at which the motor is turning. Let me increase the speed a little bit. Let's see. You see, I get so I'm going to put these functions of reading it and this function of actually splitting this data that's coming in and converting that ASCII codes to expressions in this function parse data. I split it and then I create an expression. So now once I have this function, I can just read the data. I'm going to read the data and then parse it. And so I should have I can dynamically see, as I decrease the speed, I can see the speed going down, and as I increase it, I can see it going up. Okay, but this is not exactly what I want to do. So I also like to actually visualize it. So what I do is I create a schedule task with the same thing. If the serial data is ready, I have the same code where I parse the incoming data and append it to this variable y. And if I run this, now the speed of the data, the speed of the motor is being appended to this value, to this variable y, and now I can start plotting it. So this is the speed, and if you can see the reference, and after some time the actual speed of the motor. See, I can give it some disturbance and see how if I take it off. Okay. So let me turn this off. And then finally I will remove the task and close the device. Okay, to summarize, so the kit is based on just one super function microcontroller embed code. Yeah, it provides a very unified interface. So whatever the microcontroller be, whatever the inputs and the output channel you want to use, it's just this one function that you will be using. The three arguments are the systems model, or what you want the microcontroller to compute, the microcontroller specifications, which microcontroller, which inputs, which outputs, and how they should be configured, and the upload mechanism, or where is the microcontroller and how we get the code to that. And it returns a microcontroller code data object that can be used to obtain the source code and other properties. So if you want to see what are the targets that we support, we have some entity types. Microcontroller target, so the entire list will give you what are the microcontrollers that we support, from which vendors they are, and these are the families that we currently support. So I've not been able to cover all the input-output configurations, but we have extensive documentation in the guide page and also in the new in 12 page. So I would encourage you to go and take a look at those. So for me personally, it has been a great experience developing this kit. It's all the more rewarding when these things actually work, and I hope you find this functionality useful for your projects as well. Right, with that, I think I'll wrap up my part of the talk, and I'm going to hand it over to Charles, who will be talking about the Unity link.
Thank you, Suba. I'm going to actually present Unity link, which was introduced in version 12. And well, what's Unity link? Unity link is essentially a built-in package in the Wolfram language. and it provides you functionality to integrate Unity and the Wolfram language. It's a bidirectional link. And essentially, from Unity, you can call Wolfram language functionality, or from the Wolfram language functionality, you can fully control Unity. So why is it actually useful or quite interesting to do that? First, Unity is a game engine. So essentially, most of the studio and most of the game are built using Unity engine. But from the Wolfram side, if you look at Unity, it can provide you, for example, the physics engine, because Unity actually shipped with PhysX, developed by NVIDIA. So you can actually, from the Wolfram language, call PhysX, or you can actually also use the high-quality rendering, all the real-time rendering you actually have in Unity. And also Unity have a whole lot of asset and utility in the asset store you can actually use. And later on, actually, I will show how you can actually tap to those functionalities and bring them to the Wolfram language. Now, from the from the Unity side, why will you use the Wolfram language? The Wolfram language actually provides you a powerful scripting environment, and it's actually a unique one where you can actually, open a Wolfram notebook. Roughly speaking, write a computational essay from it, document your code, evaluate and see how things work and prototype it. And you don't actually have to, really start with, C# and all the detail in, low-level programming and such. But also the Wolfram language comes obviously with all the, Wolfram knowledge base, the curated data, image processing, audio processing, geometric computation we have in place. So you can actually type on those on those functionality in the Wolfram language and use them in Unity. So if you want to create an asset, you can actually create it in the Wolfram language and move it to Unity. But also, as you can imagine, the Wolfram language have a lot of functionality in terms of analytics, as well as a whole suite of technology you can actually use, from a data drop to actually push your data, or to use the Wolfram Cloud to interact through API. So let's first start in a practical way. First, what you need first to have in your machine. Let's assume you're on the desktop, so that you can use Unity. You need first the Wolfram language or the Wolfram engine. So you can download the Wolfram engine, which is actually currently free for developer, or you can have Mathematica. And when you have them installed and you also install Unity, we automatically detect Unity and try to establish the connection. And later on, I will actually show you the documentation in case where you have issues during those setup. You can actually look at all the data. So let's do that actually more concretely. So here actually I'm in the in a notebook. So I can load the Unity link by just evaluating need Unity link. So Unity link is automatically loaded in this case, and I can actually do I actually have a little thing here. So Unity actually is starting, and you can see it on the right corner there. Essentially, it's loading. So it takes a while for Unity to start the project, but at the same time, you actually have a cell there which actually shows the progress, essentially, that we are opening Unity. So in this case, we have an example which is already embedded in the Wolfram language. It's kind of, we have a set of sample projects which can help you actually to start and play with the Unity link and Unity. So in this case, it's taking a little longer to start, so it's almost there. And as soon as Unity start and open, we'll get actually Unity there, essentially. So what actually happened behind the scene is that we launch Unity, but at the same time, we establish the bidirectional connection between the Unity engine and actually the Wolfram engine behind the scene. And through that is actually importing the package and the component. So you see that here you have Unity which is already launched and it works, and then there you have the Unity open which is done. And you can, one obvious thing you can do is you can ask, can you find me the game object ball in this scene? So you have the scene there, and then you have the board. So that's kind of the first start. You can automatically, connect an open project, Unity project from the Wolfram language. So let's start and look a little bit about the hierarchy of Unity object. And that's actually kind of affect directly the design and how we build functions. So if you keep that in mind, it's actually quite easy to see how we design and produce that symbolic language to represent Unity object. So first in Unity, you have the scene. That's kind of the fundamental part of everything. It's kind of, you can think about it as a 3D environment where everything exists. And inside the scene, you have the game object. So the game object is actually the most important object in Unity. So like if you look at the game, you have a player, essentially is a game object, or you have other part of the game, essentially the main active part in the game, actually essentially the game object. So the game object can essentially have the geometry and any other component. For example, the collision detection or physics and all the other property you can attach to it. So in the Wolfram language, what we do essentially, which actually is slightly jump there first, for a scene, you return a Unity scene object, which is actually attached to that object in Unity. And for a game object, we return a Unity game object, for example. And for components which are part of your game object, we also introduce a symbolic representation of those components. In this case, the Unity transform, which is kind of one of the fundamental object, which always come with a game object. And any other component, for example, a mesh, we have Unity mesh, you have a light, Unity light, and camera. So all those are components you attach to your game object. And the last part essentially also are the assets. You can think about it as explicit file, which are stored on your hard drive. So those also represent, we introduce a general framework to represent those assets. And you can take, a mesh, for example, and generate an asset out of it and you store it in your hard drive. And I will show some example right now. So let's actually first switch. What I will do, from this original scene, I will actually just create a new scene. And in that scene, I'm actually going to put a cuboid. So if I click on it, so I have my new scene called my scene, and I have a cuboid I call region. From that cuboid, essentially, from that scene, I can add a light. So if you click on it, you see that you have a light there. And I can create a mesh and decide to actually save it as an asset or generate an asset of it. And you see that here I have a new asset called dodecahedron. So that set of functionality, so this was essentially the main constructor, how you can create object. So now the next is how can you find the object? You also introduce, function like find Unity scene. Will return you the actual handle or the symbolic representation of this current scene. And you can take essentially that object and, for example, ask property. So that will return you the property of the object. And, for example, a property I will ask what's the name of my scene, and it tell you it's my scene, which is kind of the default name there. So this is, how to find a scene. We also have find Unity game object, which also find the game object in your current scene. So in this case, there is a game object called main camera. And also that one, you can also get all the properties quite easily, the transform and such. And in this case, actually, if you ask a property like transform, which is actually a component, we actually return you the corresponding component. So you actually have that handle. So if I click on main camera here, you have that transform component here. And again, you can ask what's the position, what's the rotation. So you actually have a direct control of the Unity editor and what's actually happening. And you actually can modify that in place. And we have the same in terms of Unity component and in terms of finding Unity assets. So from the constructor, And the search function, we also have the destructor where you can essentially take it and destroy the object or the asset. So in this case, let's, for example, remove the dodecahedron asset. So I can just evaluate this. And voila, the dodecahedron asset is gone from the scene. Okay. So we introduced actually a set of functions. So essentially, if you just think, so we have the constructor, and then we have a function to find or search those element, component, object in Unity, and we have the structure. But as usual in the Wolfram language, we try to introduce more high-level functionality. Like we try to make it more general and make it easy to actually manipulate and play, as well as we try to integrate it with existing functionality in the system. So in this case, I'm going to just show you how we actually did the integration with our visualization function, scientific visualization function. Essentially, you can take a plot. In this case, I generate a revolution plot, which is a graphic. So I have an object there. And then I just decide that I want it in Unity. So I can just evaluate it, and I call it my plot. And I say, okay, I want to create a game object out of it. So what we do behind the scene is that we take that object, we recognize that is a mesh, so it can be transformed into a mesh. So it's a geometry. So we are going to create a game object, and then add the mesh component to it. So in this case, let me first move the region here. So there you have that object in Unity. So it has the geometry and you have all the property. And if I click there, you have the mesh, and then you have all the nice property and material. We try to kind of keep up, try to preserve the look or the base shader you have in the Wolfram language, and to push the material, the corresponding material in the Unity side. So you can also essentially type in all our knowledge base where we have curated 3D objects from anatomical structure to real world topographic data and terrains. You can decide, for example, I want to get the information about the Mount Everest, the topology, and then you can generate it. And then you can take that data and then, with a click, push it to Unity, and you actually have real-world data. So I will move there, and it's actually pushing it to Unity, and then I have this call here. So let me double-click, and it's there. Okay. So I can just rotate it from here, and I have this call. And in your case, for example, Unity, actually have all the support of AR and VR. If you have just a, your VR device connected to your machine, you can actually see that object in front of you quite easily. So that's kind of that aspect, that powerful aspect of the Wolfram language, where you can actually create, contain, and especially in a programmatical way from the Wolfram code and push it to Unity. And that's kind of unique and extremely powerful. Well, I will not evaluate here where this is an example of audio search. This is kind of also an aspect where you can just take search audio on the web using our web audio search, generate the audio, manipulate it, and send it to Unity. And here you do it to Unity audio clip, which does that automatically. So this kind of show you that high-level integration where you can actually take information from the Wolfram language and you automatically move it to Unity and do the right mapping. And we build you the right object. Okay, so what I will try to do with the remaining time is just to show you a full project example we have in the documentation. And actually, let me first come back here and just, for the sake of simplicity, I will close Unity. So Unity. So actually, I should do the other way around. Close Unity. Just to close Unity. So as you see, it's a bidirectional link. So we know that we have Unity open, so we close it. So what I will do here, I will actually open our documentation, and I will look for Unity link. And that documentation also, we have it on the web, so you can actually access it if you don't have Mathematica or the Wolfram language installed. So we try to actually fully document it, and we try also to kind of preserve that mental view, that mental map I showed you from the scene to the game object to the component and asset. And also what we try to do is to show you the possible workflow from the Wolfram language, how you can call Unity, which is actually what I did there. But also we provided class functionality on the Unity side where you can just from the Unity call the Wolfram language and do evaluation. So you have that bidirectional link between both, as well as you can also call the Wolfram language or the Wolfram engine on your desktop or one version which is on the cloud or in your actually Wolfram engine which you can actually connect to. And at the beginning here, you actually see that we have a set of sample project, but also some page and information to actually help you start with Unity. So there is first the basic how the Unity work, which is that mental map I showed you earlier. But also you can resolve issue and see how to create game objects and such. So this is kind of a good source for you if you want to start to play with the two engine and play with Unity and the Wolfram language. So let's see and go to this concrete example, which is the spiky. So in this example, we are going to just show you how you can do, roughly speaking, build the whole scene and the whole animation from the Wolfram language without even having to write some C# script on the Unity side. So I will just move that on the side, and I will just start by evaluating or loading Unity link, which is already loaded. I will create here a project called Spiky Rain. So I do a Unity open, so it's automatically connecting to Unity, and it's loading the asset and establishing the connection between the two engines. So that's take a little bit time for Unity to actually start and install everything and compile the base modules. So, but as Unity is opening, next what we'll probably do is then we're going to start to create just a basic structure, just to have a nice project. We're going to create a 3-asset directory. One which will contain the scene, one will contain the mesh, and another one will contain the material, just to kind of nicely organize our project. And as you see it, right, this is kind of all programmatic, so you can actually do it and restart and rebuild the project. You don't have to be on the Unity side and try to remember what you did and so. So you can actually document your project like we do in this case and be able to reproduce it. So here I will create the Unity asset. So if I come back down here, I see the 3 assets already here, the material, mesh, and scene. And by the way, this additional assets, not additional asset, this is actually the Unity package. This is the Unity package, the Wolfram Unity package, which actually allow the connectivity between the Unity the Unity editor and the Wolfram engine currently, which both are running. So you have it in your project, and at the end of your project, if you don't need it, you can actually delete it if you already you don't really need that connectivity anymore, but you need it to actually work with the Unity editor. Okay. So now I'm going to create just a file, a scene, sorry. And I can actually set it as a file, so it's actually going to save it. And I will create a mesh, which is actually coming, which is our spiky, and it's a boundary mesh. So I'm using here polyhedron data for that. And then I create a plane. So if I click there, I get the plane in Unity, and I call it platform. And here we have the property, from the earlier angle as well as the local scale for the plane. And now we are going to create, a bunch of spikies. So in this case, we generate some random position, generate some random color, and generate material out of it. So if you come back to Unity here, so we have the symbolic representation of the material here. And if you come back to material directory, you see all of them here, spiky 1 to spiky 10. And now I can take those meshes and then create a game object. So I create, there are a bunch of game objects. You could actually go ahead and create a prefab and then do the corresponding thing. But in this case, we just create, for the sake of demo and simplicity, we just create a bunch of game objects. And now from those game objects, you can actually assign property. So in this case, we take the game object, and then we set up a position, and also we set up the material and the scale. And also what we do is that to actually do something more fun. We actually add some physical property to it. So here we actually add collision detections. So we create rigid bodies and assign them to each object with the mesh collider. And to just make the scene nice, we delete the default directional image. So there it's happening. And now we actually create all the additional light we attach to every object. So I will save the scene, and now I can, from the Wolfram language, ask Unity to play it. So if I click there, so Unity behind the scene is compiling, and there we see. So we have that nice animation, all built from the Wolfram language. You can actually just stay in the Wolfram language and stop the animation. And what we actually add even more, as I point you out, we actually want to add more top level, high level function. So what we added is actually a Unity build. So that function allows you to just, in one line, compile your game and have an executable. So in this case, it's compiling, the spiky ring. So you take all the information from the scene to the material and assemble it appropriately and pass it to Unity to actually generate it, and it's successful. And if you open the summary box, it tells you where the location of the object is. And in this case, I just do system open, and I ask, okay, can you actually run that? So I get that information of spiky ring and play, and then I have actually a standalone animation of my spiky. Okay. Yes. Okay. So this is a nice example of how the functionality from the Wolfram language, how from the Wolfram language you can actually, interact with Unity. So if I just go back, we also have an example in this case where from the Wolfram language, from Unity, you can actually call the Wolfram language to our cloud API. So what I will suggest you is to go and try it. You just work out of the box, you evaluate it, as long as you have Unity installed, and you should be able to actually play with that. Okay. So what I want to point out, before I close this presentation, is that Unity Link allows you full access to Unity functionality, and we try to do that through high-level function in the Wolfram language, and we provide you symbolic representation of each Unity object, so that you can actually have a full control of Unity. So that includes from the C# class to the actual menu editor, where you can open it and control and script actually all your interaction with Unity. And also we try to make sure that you can easily exchange the data from Unity to the Wolfram language. And you can take advantage of all the curated data and different areas we have in the Wolfram language to actually facilitate your development, if from a game to an animation to a project you can actually want to build. But moreover, which what I will not discuss in this case or not present in this case, we actually also allow you to type directly to the cloud, launch Unity in background. For example, if you want to do automate testing for your game, or generate C# code, so that you can embed it and call our Wolfram our cloud API, for example. And there is a lot of more functionality. So what I will suggest is go to our web page, the Wolfram language page. You get a lot of information there. I showed you already the Unity Link documentation. And also what we hope in the next future is we'll see a lot of blogs, like blogs, and as well as information from our community you can actually see actual project. So if you stay tuned in the Wolfram community, you actually see some example on how people use Unity. So there's a lot of information for you to start, as well as a lot of demo to play with. Okay, so well, that's conclude my presentation, and Abdul is next, and we will talk about the compiler. Thank you.
So hello, my name is Abdul, and I'm going to be talking about the new Wolfram compiler. So, and this is a feature that we introduced in Wolfram version 12. So the outline of this presentation is I'm going to talk about the usage and syntax of this new Wolfram compiler. Then I'm going to talk about how the compiler is implemented, so a high-level view of the pipeline. Then we're going to use the compiler to leverage pre-existing language features and also generate and save code. And then we're going to talk, finally, we're going to talk about future developments. So the new compiler, so there was an existing compiler from Mathematica. We decided to start a new compiler, and it's designed, because it's designed from the ground up, this version, to be seamlessly interfacing with the rest of the Wolfram language. In fact, the compiler is written in the Wolfram language. It's extensible so that users can add new functions or new types, so extending the compiler by developing libraries or data structures. And the idea is that we're going to continuously upgrade and develop this compiler further. So this is a long-term project. We're just previewing it in version 12. Right. So the syntax of this new compiler is you have a function compile option, and that takes a function. And if you evaluate that, then what you're going to get as output is a compiled code function that then you can evaluate. Now, the structure is that you have your function, and you're going to define types on the input arguments. So, for example, in this case, I'm going to talk about, I'm going to say that arg1 has a type of integer 64, and arg2 has an integer 64 as well. Now, note that the intermediate operations, you don't need to define the types of. There's a sophisticated type inference mechanism, which will deduce that the plus that here means it's an integer addition. Now, why did we develop the new compiler? Well, the old compiler has been introduced since version 2, so that's more than 20 years ago. And it wasn't extensible, so you couldn't do certain operations. So in this new compiler, we extended the support of the number of Mathematica constructs or Wolfram language constructs that you're able to express. And it plays nicely between in languages, you have usually compiled code that's, you want it to be highly performant code, and you have some sort of visualization or some data filtering code that doesn't really require to be as performant. So with the compiler, you can have a marriage between the two. So in this case, I'm computing the Mandelbrot set, and the Mandelbrot set is very computationally expensive, but I'm leveraging the existing tool like density plot to plot the results, which is not as computationally expensive. And with this new compiler, you can express things that the old compiler was not able to do. So for example, recursive functions. So in this case, I'm defining a factorial function. So I have a factfun, which if the input is 1, then I'm going to return 1. Otherwise, I'm going to multiply that argument by recursively calling this factfun with arg-1. And if I call that, then I can call this function. And note that it's the same as if you would have called the factorial function within regular Mathematica. And another feature is that you can compose these functions. So again, a limitation of the old compiler is that you weren't able to quite compose your functions, but in this case you can. So let's say I want to do a bisection method, a root finding method. So I can define a function generically that takes any function that has a signature of a real goes to real. So things like sine or cosine or tangent. And it's going to take a starting position and ending position. And this function is generic. It's just taking another function as input. So let's say I want to say the input function is a sine function. So then I can do the compile that sine function, and then I can pass that into the compiled expression. Now, the compiler pipeline follows a traditional compilation pattern where you have a Wolfram Language AST that then we transform it to a desugared form, so a more primitive AST. So things like table and map might get reduced to something a bit different. Then we generate some intermediate representation. So this is very close to assembly. It's not exactly assembly, but it's a machine-independent assembly language. Then we do a type inference on that, and then we create the typed version of this intermediate representation, and then we generate executables. So this is talking about the same thing. Notice that we leverage some pre-existing and quite popular tools like the LLVM IR. Although we're not typed into the LLVM IR, we're generating, the default is to generate LLVM IR, and we can generate JIT code, so just-in-time compilation, or do ahead-of-time compilation by generating libraries. And we can target other backends like JavaScript, C++, and the Wolfram language, and we're exploring those for future releases. So the structure of the compiler is it does a transformation in terms of what we call passes. So it's a pipeline mechanism. And in this case, you have a Wolfram language, then you're going to create some expression, you're going to do some analysis. And there's a lot of these analysis that you could invoke. Now, all of this is hidden behind the scenes for you, but you can also invoke them directly if you so choose. So there's about there's a few hundred of those sort of passes. And these are optimizations or transformations that you need to do. Now, what can you do if you have a compiled function? Well, one thing you could do is you can save it. So the idea is that you don't need to go through this compilation mechanism every time you want to use the function. So you can save the output in terms of assembly. So this is machine code, x86 assembly because I'm on a x86 system, or you can generate LLVM IR. So LLVM has its own intermediate representation, and this is the sort of another representation. Or what might be more useful is you could generate a library. So in this case, I have a function which adds 1. I'm going to generate a library. Then I can essentially say library function load, and that's going to load that library into my current session. So these two could be in multiple kernel sessions. So let's say I compile a library, and then I can send it to a bunch of systems, using the cloud, or not the cloud, the grid Mathematica. And then I can load these in each one of these subkernels. I can load the function, and then I can do the evaluation. And you can also generate code for exotic architectures, like, for example, WebAssembly or CUDA. You can generate code for those as well. Now, we don't have tight integration with those sort of exotic systems, but we actually have prototypes, for example, integrating with WebAssembly or CUDA. And those will be introduced in potentially future versions. Now, one of the questions is, what systems are, what symbols are supported, or which functions are supported? And there is quite a few functions that are supported, mostly centered around numerics, but you can extend those as well. And there's many more internal system sort of that we support. So the compiler is built on top of Mathematica, and it needs some more primitive functions to do some of these operations. Right, so to kind of tie that into the first session, let's say I want to do an external evaluate. So I have a function that is in Python, but I want to call it from within my compiled code. So as Todd showed, you could use external evaluate to evaluate 2 plus 2 in Python, and you get 4. Great. So now I'm going to build a function which takes 2 arguments, and it's going to use a string template to construct a Python program that adds these 2 arguments together. So this is a regular mathematical function. If I pass in 20 and 30, I'm going to get 50. But now I want to call this from within, my compiled code. So let's say I have a very complicated code, but I need to use some Python library or some external functionality, or maybe the Unity engine to do the evaluation. So that's where there's a function called kernel function, where you just annotate the types of the input, and you can call these functions from within the compiled code. So Python is the sort of function that we defined, which does the external evaluation. And I can evaluate this in Python, so from within compiled code. So this kind of is important because there's some functions that are inherently in Mathematica and the Wolfram language that that are hard or impossible to compile. Now, you can also kind of go to the flip side. So there's a lot of algorithms that require some constant data as a seed to do the computation. So for example, we want to do primarity testing. And for that, you need to get the first few primes from a seed. So these are traditionally specified as constants if you write this code in C or C++, but we can leverage the Wolfram language to essentially get these constants programmatically. So this function, this code essentially injects some variables into the program, and it's going to compute the prime, whether a number is prime or not, using some primarity testing algorithm. So in this case, if I do the evaluation, I get a compiled function, and then I can check if is 17 prime. Right. The other thing is you could integrate with other sort of system like dynamics. So here I have a function that computes the game of life board, setup at a single iteration. And then I can generate an initial board configuration, and then I can dynamically plot the results using array, plot, and dynamic. Another sort of interesting thing is that you can compose bigger, you can write bigger code. So for example, in this case, I have a quick sort function which takes a packed array or a list of machine integers of rank 1, so it's a vector of integers, and performs quick sort. Now I can then essentially perform the quick sort. So I get I'm going to generate some random integers between -100 and 100. So I'm going to generate 20 of those, and then I can sort them. Now it is kind of neat to look at, does it work for larger inputs? And the answer is obviously yes. Now, there's a lot of documentation on the documentation page about how to use function compile, and there's a lot of knobs and switches that you can use to configure, or tweak your compilation. So the Wolfram Compiler, in summary, is a new execution path for the Wolfram language. It uses innovative and important programming technologies, and it allows you to, have a path towards compiling your code. So you don't have to compile your entire code. You can have some kernel functions, spreading out in the code, but you can have larger parts in compiled code. It supports a lot of variety of types, so atomics, like strings, list containers, data arrays, and things like that. Functions. It has support for the Wolfram language. So you can call Wolfram languages from within the compiler or vice versa. You can have a lot of different output targets. And for example, you could do ahead of time compilation. So you can compile and ship libraries to users. It has this callback to the Wolfram evaluator. And it uses the LLVM to generate machine executable code, and this is a typical design for the compiler. And it's released in Wolfram. It's released in Wolfram version 12, and we're constantly updating it. And we plan on essentially providing updates every few months as new developments and new compilers get released. So in future developments, we want to make the compilation faster. So that's a big hurdling block. But we've made it quite faster in version 12, but we want to make it much, much faster. And for that, we want to compile the compiler. So that's a big test for us is, can we compile the compiler, which is itself is written in the Wolfram language. We want to add more ability for users to define types and have proper standalone support. And we want to support other sort of exotic platforms like CUDA and WebAssembly. And we're going to want to leverage these compiler methodologies to allow users to, have better things like editor support or linting or analysis. So that would be, helping the programmer, write functions, or how to do computation, or provide syntax warning or partial evaluation and code generation. So with that, I'm going to give it to Christian, who's going to talk about blockchain.
Right. So thank you for joining today. I'm Christian Pascal, Connectivity Manager at Wolfram Research South America. And today I'm going to make a quick overview of our new blockchain functionalities and basically talk about how to read and write data to blockchains. And so actually not all these functions are new, but we added more support to them. So let's talk first about blockchain data. So this function returns general information about the network. And when we introduced this in 11.3, we only supported Bitcoin and Ethereum, but now we not only support the mainnets, but we also support the testnets, which is super useful when you are trying to do experiments with all these functions and to learn from this blockchain. So, for example, here you can see, and let me show this as a data set so you can have a better view of what we have here, the properties. So you see here we have the mainnet and the testnet for each of the blockchains, and some of them have specific properties for them. So one of the things we always try to do is not only to return data, but also to return computable data. So like in this case, for example, I'm going to just take this quantity here. So actually, if you see the full form, you'll see that the quantity has associations in units. And I can start doing computation with this, like I can convert this to, say, US dollars, or to a more, I don't know, to a more exotic currency like Peruvian soles. We also support cryptocurrency. So if I want to convert this to, let's say, Ripple, that should work. All right. So yeah, this is just general information about the network. So what about blocks? So let's talk about the blockchain block data function. So this function here returns information about the specific block. So the first argument is the block height or hash. In this case, if I use -1, I'm going to get the latest block of the blockchain. And something I didn't mention before that I should mention here is that the blockchain-based option is the one you use to specify the blockchain you want to interact with. So in this case, you can see information about this specific block. And so let's say I'm going to extract one particular property. So let's say the byte count. So the byte count is basically the size of the block in bytes. So we'll track this from the Bitcoin mainnet, and we'll do the same thing from the Bitcoin testnet. And from here, I can do anything I want. So like I can do like a bar chart to compare these blocks, or do basically anything I want with that information. So let's do something interesting that I think is super useful when you want to use all these Wolfram language power from other systems. So let's talk about APIs. So I'm going to first create a very simple function. Let's call this block size. And my function will return the size of this block. Let's just use the Bitcoin mainnet here. I not only want the number. Let's say I'm going to return a string and say here something like the size of the block is this, and then to send here something like bytes. All right, so if I try this with, I don't know, block 1, 2, 3, 4, 5, 6, I get the result. If I try with another one, I get it. So this is fine. This is working from the Wolfram language. But what about if I want this to work from another place? So we have this very powerful function, API function, and that allows me to create instant APIs. So I'm going to create one API that receives one parameter called block. It's going to be an integer. And what I'm going to do with this is I'm going to return the output of the function I just wrote here, like this. And now I'm going to deploy this to our cloud. Let's call this API test and set the permissions public. All right, so I now have an API. So let's say if I go to my terminal here and I curl this API and I provide the parameter, it was called block. So let's try again 1, 2, 3, 4, 5, 6, and I should get the result here. Again, I can try with other block. And so I can do the same thing from any other language that supports HTTP requests. It could be Python or C or any other language. All right, so we talked about blocks. And what about transactions? So we have the blockchain transaction data function. So the function is very useful to inspect transaction details, and we'll try to return all kinds of information about transactions. So remember, I mentioned before here the blockchain-based option. So let's say in this case, I'm going to stick to the Bitcoin testnet. I'm going to do some experiments here. So I also have the variable $blockchain base. If I set this to, in this case, for example, Bitcoin testnet, this will set the default value for the blockchain-based option. So I don't have to use this option anymore. So remember we had this block here. So it was output 16. Let's see. Right. So from here, want to extract the transaction list. So the transaction list in this block is basically the list of all transactions included in this block that was mine. So I'm going to remove the Coinbase transaction and do a random choice of this. Let's call this random transaction. All right. But remember, this is from the mainnet. So for now, for my experiment, I just want to show you this using Bitcoin. And you can see here, again, a lot of information about the transaction. So one new thing we have here is that we provide now a lot more information in the case of Bitcoin, for example, and the inputs and the outputs. Here you can see the complete script. So for example, you can see this is a standard page-about key hash script. You can see the unlocking script in this case, and more information that can be very useful. All right, so I wanted to do I did something some months ago. I encoded data in the Bitcoin testnet. So I have the transaction ID here, and let's see. I don't remember when I did this, but let's find out. All right, so this transaction is from February, and what I actually want from here are the outputs. So remember, I was showing you how we provide a lot of information from the outputs. So I'm going to extract I want the outputs of this transaction, and you probably don't see anything weird right now, but let's if I extract just the amounts, sorry, okay, if I have here all the amounts, this is where I encoded the data. This one is the change I sent back to myself. So I'm going to remove this, and I'm going to save this as amounts. Okay, and now I'm going to play with this data I just got from the blockchain. So as you can see here, you have we have quantities with Bitcoins as units. But I don't want the units right now. I just want the magnitudes. So I'm going to just extract the magnitude, and I want this in an integer form. So let me multiply this. All right, and run the result. All right, and finally going to get the integer digits in base 2. All right, and I'm going to save this as digits. And finally, so I want to normalize this for all these ones and zeros to have the same length. So I already have a code to do that. So you may be wondering what's in here. So if I execute an array plot of all these, you'll find something I hope you are familiar with. And if not, let me show you what's this. So if I run 15 steps of rule 110, you see that I encoded this cellular automaton in the Bitcoin testnet. Let's actually compare these two results. Yep, they are the same. All right, so how did I encode all these? That now we can talk about writing data to to the blockchain. So before we talk about it, oh, by the way, so if this wasn't clear enough, I'm just seeing one question from the audience. So this function here is this program here is basically the equivalent to doing something like a URL execute that it's going to fetch the URL I provided here. All right. So before we talk about writing data, something very relevant to blockchain is cryptography. So we are introducing new cryptography tools in version 12. We already had some, but now we support elliptic curves. So I'm going to generate a pair of private and public keys using elliptic curve, like this, and I'm going to do something really cool. So we have now the blockchain key encode function that can use a private key or a public key to return different things. So in this case, what I want is I want to encode this public key as an address, and I can do this with different blockchains. If I do this with Bitcoin, you'll see it has the form of a Bitcoin address on mainnet. I can do the same thing with testnet. But for this particular example, I want to do this with the Ethereum testnet. So let's call this my address. All right, so let's try a quick experiment here. So I have an Ethereum faucet. This is a testnet faucet. So I'm going to send some ether to the address I just created here. All right, so it is dependent, so we can actually check that from here. So I also have the blockchain address data function that will return information about this address. Oops, I have to use the Ethereum testnet. Okay, since I received the ether now, yeah, it's been mine. All right, so I have now ether in this account, in this Ethereum account I just created, and now I'm going to create a new pair of keys. So let's say generate symmetric key pair. Also, if you go to our documentation, our methods are documented here. In this case, elliptic curve we support is the one used for Bitcoin and Ethereum, but we are working on to add more curves. All right, so let's create another pair of keys, and I'm going to use my code here, but in this case, it's going to be the let's call this destination address. I'm going to use the public key here to encode a new address on the Ethereum testnet. All right, and now if we check this address here with the blockchain address data, it should be empty. Yeah, it's empty. So I'm going to create a blockchain transaction and send some ether from this account to this account. So I don't have to memorize the whole thing. We have everything documented, and we try to add common examples here. So I can use this one, and so this is a symbolic representation of a transaction. So let's call this new transaction. In this case, the transaction count is 0. This is fine as a gas price. I'm going to send this to the destination address and send this amount of bitcoins. I mean, of Ether. All right. So I was saying this is just representation of the transaction. It hasn't been sent to the Bitcoin, to the blockchain yet. So the first thing I have to do is I need to sign my transaction. The same thing is valid for Bitcoin as well. The form is different, as you can see. As you can see here, this is a Bitcoin transaction, and then this is an Ethereum transaction. And we're working on supporting more blockchains. So each transaction will have its own specific properties. All right, so let's sign this transaction. So I have the blockchain transaction sign function that will sign this new transaction. Remember I had this pair of keys. So I'm going to use the private key from here. And as you can see, the object, the blockchain transaction object, changed a bit. Now it has the icon is different and the property sign is true. It is still not in the blockchain. So for that, I'm going to use the blockchain transaction submit function to send it to the Ethereum blockchain. In this case, the object has the information about the blockchain, so I don't need to specify that this is for the Ethereum testnet because it's already here. So, all right, so let's try to do this. And this has been sent to the blockchain. And if I get a transaction ID, let's call this new transaction ID. And I can do something like blockchain transaction data and see if it has been mined. Let's see. And I probably need to specify blockchain-based Ethereum testnet. Well, it seems it has been mined. So let's see so remember we have this new address with 0 balance. So if I run this again, let's try it here. So I should get, yep, I have some money now here. All right, so we are always working on adding more blockchains, more support to blockchain functionalities. So it will be very useful also to get feedback from you in the polls and in the comments, the questions, to see what kind of things you would like to see from blockchain integrated with Wolfram Language. Also, so I'm receiving some questions here about Bitcoin price. So we use different feeds to get the Bitcoin price, and about Brain Wallet keys. So we currently support just generating keys in the way I showed here, but we are working on adding more support to different types of keys and ways to create keys and eventually wallets and more things. So yeah, that's all for now. Thank you very much. And I hope you use all these and it's helpful for you. Thank you.